Living our busy lives in cities like the majority of us do, we sometimes lose touch with foundational things that have huge impacts on our lives. It might be the farms and ranches that supply our food, mountains that feed our rivers, or oceans with their vast importance. In this video, we will explore these strange objects and how they affected geology and the resulting impact on the history of humans and animals. One of the very first projects I was asked to do as a young geologist was to investigate some wells, pretty deep wells, about 12,000 feet or so deep, that were producing natural gas at high rates from, it looked like really thin units or beds, formations, say 10 feet thick or so, which is quite thin. And they wanted to know more about it. And boy, this was quite exciting for me to think that they're asking me to do this. And they said, just figure it out, would you? And of course, I wanted to look at the rock, the actual rock. Boy, I'm a big believer in that. So I went to look for core. It turns out you can use special tools and cut cylinders of core way down in this hole that you're drilling and extract it. But it's a very expensive process, so only a few wells have that core like that. Turns out none of these wells had core. So I had to go to my second position, which is find the cuttings. Now cuttings are the pieces of rock that are broken up as you drill the well, and they circulate up the hole, and a geologist on site collects these cuttings every few feet, and you have a record of the rock, these chips of rock. The chips are, typically the size of my small fingernail here or so. And I thought, you know what I can do? I can take these chips of rock, I can put them in a pool of epoxy, blue epoxy, and put it under vacuum, and all that epoxy kind of sucks into all the pores and holes in the rock. You let it dry, and then you can grind it down really thin to 30 microns is the standard thickness. Now, a sheet of printing paper is about 100 microns, so these are really thin. And once you have that, you can look through your microscope and see all kinds of wonderful details. And I had a lot of experience this in my graduate work that I had done in school. There was a professor that was really good at this, looking at all different types of rock, and taught us, these rock types. Boy, it was so exciting for me, because I get these samples and I'm thinking, what am I going to learn? And I look through my microscope and I look and I look and I go, what I'm seeing, I don't know. I have no idea what it is. What is this about that I'm looking at? It actually was a bit depressing, because I thought I knew it all at that point as a young geologist. I'd seen so many different rocks in thin section, but I hadn't seen anything like this. And what I saw was very similar to this image. Remember that the blue epoxy fills the holes or voids within the rock. So that's where all the natural gas was stored, and that's where it was coming from. And of course, what I was focused on was the shape of these holes. Notice you kind of have two basic types, some that are very round looking, very circular, and others that are long and skinny. And sometimes you even see ones that seem to have a branch on them of some sort. I remember thinking to myself, how is it that we have holes with these kinds of shapes? How were they created? I was a bit stymied here. I had to figure out what I was looking at. And boy, it was a puzzle. I was looking at papers, research papers and things, just kept digging. And a geologist told me about this book. And he said, Myron, I think this book might help you. Take a look at it. And I bought this very book here a month or two later. This was the company's version that I was looking at the time. It's called A Color Illustrated Guide to Carbonate Rock Constituents, Textures, Cements, and Porosities. Oh, that's a mouthful. AAPG Memoir 27. And I just started thumbing through the pages. And they have, let me show you a typical couple pages here. They're photos of various rocks in thin section through the microscope. So I thought, boy, I hope I find something. I'm going through, and I came finally to page 51. 51 and 51, and looked here, and lo and behold, I saw exactly what I was looking at. I knew immediately that's it. And then I started reading about what I was looking at, and it kind of blew my mind. Let me show you why. It turns out what I was seeing were tiny pieces of this. Turns out this grows on the ocean floor, typically in very deep waters, thousands of feet of water. They're made of silica, glass, amorphous silica, or sometimes they call it opal amorphous. So it has no real crystalline structure to the silica, to the quartz. It's kind of a form of quartz, I guess. It is silica, but it's amorphous. This thing is super lightweight. It only weighs 6 grams, which is the weight of a sheet of paper, ironically. I keep using sheets of paper, printing paper. It's very sturdy. And this is what I was looking at. And it's a sponge, a siliceous sponge. Turns out most sponges are siliceous. Boy, this really got my brain a-going. Although sponges may look like plants, they're actually animals that attach themselves to the seafloor. They feed off of microscopic organisms within the seawater as the water passes through their structure. Some species of sponges are thought to live many thousands of years. They first showed up in the rock record about 550 million years ago, so they're some of the earliest forms of life. They really get interesting when you learn about how they're built. Let's zoom in as far as we can go with a scanning electron microscope, or SEM. They don't have a crystalline structure, rather they're composed of blobs or spheres of silica. Interestingly, gem-quality opal has a similar internal structure. With the right size, shape, and arrangement of spheres, you can get the beautiful colors. Stepping back, we can see that these siliceous sponges have some fascinating networks of glass fibers. But for the most part, they're actually not fibers. They're individual glass components named spicules, sponge spicules. These drawings show well the wonderful variety there are in the shapes of these spicules. And the wavy brown line on the left side there represents a human hair for scale, so these are very small features. And here we have SEM images of various sponge spicules. Aren't they just wonderful? Remember that when you zoom way in on the silica of these spicules that we see here, you see these tiny spheres. Let's take a closer look at this sphere-shaped one. Wow, just mind-blowing, isn't it? Looking at this beautiful structure of siliceous spicules, one has to wonder, where did the animal live? It turns out that the spicules have concentric layers within them, kind of like tree rings, and they alternate between silica and living tissue. Unbelievable. I have something I want to show you. It's about a 4-hour drive to Casper, Wyoming. But I enjoy the drive. There's so much geology, and I think you're going to find this very interesting. Driving through Wind River Canyon never gets old for me. It gives me a chance to think about deep time and see some really spectacular geology. I just love this canyon. I finally made it here to Casper, Wyoming, to the Casper College, the Tate Geological Museum. It's a wonderful museum. Lots of really neat specimens here, and fossils and rocks and minerals and all that stuff. So it's a great place to come visit. But the primary reason I came here was for this wonderful mammoth right here behind me. It's a Colombian mammoth. They named it D for that was the name of the heavy equipment operator that bumped into it when he was doing some work. And they excavated it, and this is the largest Colombian mammoth ever found. It stands nearly 14 feet at the shoulders. I mean, this is a really mammoth. It turns out these mammoths appeared on the scene in the fossil record in the Western Hemisphere about 12 million years ago.
and then they disappeared, became extinct around 12,000 years ago.
The work the paleontologist did on D revealed that he was very old, somewhere around 60 years. He had worn teeth and likely died in the winter of starvation. The poor old fellow just couldn't get enough food chewed up. He died about 11,600 years ago, which is right about the time when mammoths became extinct.
Why would Myron come here to show you a mammoth? Well, let me reintroduce our sponge. Our friendly sponge. It turns out that the lives of sponges like this and mammoths are intertwined. How could they be intertwined? Well, let me show you a couple more things. A nice sample of chert here. When you get these red-orange colors, jasper. And here's some chert here that's a darker color, which is called flint. They're both cherts, but many of the cherts around the world are made from siliceous sponges. That's their origin. And how that occurs is a discussion in the future here, but these cherts, many of these cherts come from these siliceous sponges. And we know what happens with this type of rock. Natives made tools of various types. They made weapons and knives and awls for poking holes through hides and things like that. Many different types of tools come from this chert. And I have a special one right here in my pocket. This beautiful spear point is an authentic one that came off a buffalo jump in Montana, made from this very chert right here that I have here, or the same type of chert, I should say. And it's younger. It's not the real old one, the Folsom points that would have been used on a mammoth like this, but it's younger than that. But nevertheless, it helps us understand how the natives used chert to their advantage.
This obsidian shows nicely a property that chert also has. It's called conchoidal fracturing. Natives learned to take advantage of this property by chipping away at the rock, creating knife-like edges in a process called knapping. This flint spear found at a buffalo jump shows just how skilled they became. With backlighting, you can see just how thin and sharp the edges are. It's incredible that this very spear point was used to kill buffalo.
A quick jump to another museum in Greybull, Wyoming. It's close to near where I live, a small community museum with some marvelous specimens here to examine. It's a free museum. I recommend you come by and check it out. But the reason I came here was to show you some nice examples of artifacts, native artifacts made from chert.
Beyond the obvious arrow points, we have an awl here used primarily for punching holes in leather, 3 knives or scrapers used in the butchering process, and these 2 modestly worked ones. I included this beautiful piece of jasper because it reminds me of this amazing Folsom point from Utah. Folsom points are 12 to 13,000 years old and would have been used to kill mammoths.
I can't imagine hunting a huge animal like this mammoth, this Columbian mammoth, with spears, with points like this. Seems almost impossible, doesn't it? Boy, it took a lot of bravery. It's just amazing to think about.
In my view, healthy adult mammoths were not hunted. It would have been too dangerous of an undertaking. There were many other animals available to hunt that wouldn't have presented such danger. That said, young or old mammoths, or ones trapped in a bog or something like that, certainly would have been pursued. There are many sites that prove mammoths were killed and butchered. In fact, a well-documented site is near the town of Worland, Wyoming, called the Colby site.
But coming back to these various cherts and how they've formed geologically, I hope you're thinking, well, how can you go from sponges, these hairline, super fine spicules and things, to form this chert? And that process, I think you're going to find to be very interesting.
Now to the fascinating geology of cherts. How is it that layers of chert form? Or how do nodules that protrude from limestones form? I mentioned that much of the chert comes from sponge spicules, but now I want to introduce the 2 other major sources of biogenic silica. The first is radiolarians. They're microscopic and are single-celled protists. They sure make beautiful shells of silica. They first showed up in the rock record about 540 million years ago at the start of the Cambrian. The second additional source of biogenic silica is diatoms, which are microscopic single-celled algae and have been around about 200 million years.
We've made it to a whiteboard discussion, and this is a cross-sectional view, so I guess I better draw my tree. I don't want to disappoint some of you out there. So here we have our tree here. I'll put it right here to make sure we know we're looking sideways. And this is the ocean here, and of course the deep ocean out here. And these goofy looking things here are sponges that I've sketched in here. And all these dots would represent radiolarians and diatoms living their lives out in the ocean water. Now, a question I want you to think about is, how would you form a layer of chert with this in this scenario that I've sketched here? At first, that seems relatively simple, and in some ways it is. Well, you just have sponges living out their lives and dying, and these sponge spicules accumulating in mats of spicules. And maybe they're alone or dominate the silica deposition, but it can be combined, of course, with radiolarians, or if it's younger than 200 million years, these diatoms. And they just build up layers of this. This is referred to as a siliceous ooze, by the way, by geologists. And okay, so let's put in our siliceous ooze as these animals and protists die. Here we go. So I'll put in a layer. They accumulate along the ocean floor in this layer here. And there you go. But there are a couple twists we need to contemplate. Yeah, geology, there are always these complications. In fact, I find that every case is essentially unique. But we have to think about this a little deeper. I've got something for you to ponder. Let's think about this a little more. I'm going to focus on radiolarians and sponges and sponge spicules. The sponges are dying and these spicules accumulating through time, and we have the radiolarians living out their lives and they die. And then their skeletons start drifting down to the seafloor. And I've got something I want to tell you that's really kind of cool about these skeletons drifting down. Question: how long do you think, once they die, that it takes for them to drift down to the seafloor? You got some thoughts? You know, I wish we were all in a big old auditorium and I could call on one of you. Let's say there's one of you out there. Jim. Okay, Jim. You're out there. Jim, how long? How long do you think? And Jim, he's kind of nervous. I've done this, by the way. I've been in these auditoriums full of geologists doing this very thing. And Jim, he's a bit nervous. He says, a couple weeks. And there are people in there that are going, my word. Other people in the audience going, gosh, I was thinking a couple days. Could it be a couple weeks? And there are other people in that audience that are going, gosh, I was thinking maybe it could take a couple months. And you know what they do? They all start anchoring. It's a process called anchoring. They start changing their thoughts because of the very first person that announces their guess. And it is a guess. It might be an educated guess. And they anchor in on that. They're reluctant to stretch beyond that first guess that Jim made. And so the best thing to do if you're trying to get a feel for the spread, the variability using people, and sometimes you need to do this, then you have them all write down their thoughts without any input from anyone else. And then you get a good breadth of what it could be from the shortest time in this case to the longest time. So I'm going to anchor you guys out there listening to me. I'm going to say 6 months. What do you think? So there you go. People start anchoring, right? Well, let me anchor you again. Let me throw another one at you. Could it be 10 years? How about 20? Well, how about 50? 20 to 50 years is what they estimate for these siliceous skeletons to drift down to the seafloor. Isn't that kind of fascinating? Well, now we've got to get back to it here. So we have them accumulating on the seafloor, these siliceous elements, I'll say. But there's something else going on at the same time, isn't there? There's sedimentation, background sedimentation. After all, we have rivers coming into the ocean. We have carbonate deposition going on that can be occurring. And this is what I'll refer to as background sedimentation. And wouldn't that be contaminating this layer as you have sedimentation going on? So there you go. And it leads you down some fun mind thoughts to think this through. And well, okay. So you need a high production from these sponges. It's got to be great condition, or for the radiolarians, or both, or whatever it might be. You need great conditions, so high production. Well, that certainly helps, but you still have, contamination. And in fact, at first pass, you would think that the background sedimentation would be higher than the accumulation of these skeletons. I mean, that's got to occur very slowly, even in high productive zones, it seems. Yeah. And I mentioned also sponges, at least some species are thought to live thousands of years, so that adds more to this. Well, where am I going with this? Yeah, high production, sure. I'm going to throw a new term out for you. It's called a starved basin. Well, starved, there you go. You have situations, starved basin. Geologists use that when it's starved for sedimentation. There's very little sedimentation going on at all. And when that's occurring, this background sedimentation, it's just in a situation like that. Then things like radiolarians and sponge spicules can accumulate into these layers of ooze, these high percentages of siliceous skeleton material.
The well-known Arkansas and Oklahoma novaculite, a high grade of chert, was deposited in the Devonian and Mississippian ages from about 416 million to 318 million years ago. The rock formation containing this bedded chert and shales interbedded together gets up to about 900 feet thick, really impressive. The chert was metamorphosed, which made it into this extra hard variety known as novaculite. As you probably know, it also makes a great whetstone for sharpening knives. In West Texas, near the community of Marathon and also down into the Big Bend National Park area, there are prominent ridges formed by a novaculite. It's called the Caballos Formation. It was also deposited in the Devonian and Mississippian and is about 700 feet thick.
The other bit of a puzzle that we need to come to grips with is that, chert is made of microcrystalline or cryptocrystalline quartz would be a better word. Super small crystals of quartz, just regular old quartz. That's what it's made of. And we've learned that biogenic silica is made of these spheres or blobs of silica. So there's something going on there, isn't there?
It turns out that biogenic silica is quite unstable, so it either starts to dissolve or convert to quartz. It goes through phases of quartz called cristobalite and tritomite, and then on to regular old quartz. Chert is super small, has super small crystals, cryptocrystalline. The size of these crystals is 8 to 10 microns across, as seen here in this thin section.
Time to discuss chert nodules, these weird blobs of chert that so many of us are familiar with. They can be quite beautiful, pretty cool to look at and find. And of course the natives used them as well to make their tools. But I've got a cross-sectional view, and with layers of, in this case, limestone. Chert nodules are most commonly found within limestone, but they can be found in sandstone and shales. And I've sketched here a series of these red blobs here, chert nodules, and in this case they're along a bedding plane. They're along this line that's parallel to the formation boundaries. Other cases, they seem to be somewhat randomly distributed within a layer of limestone or sandstone or whatever. They can also be kind of lenticular shape or long little layers of it, thin layers that come and go, things like that. So in general, we refer to these as chert nodules. Another thing that we can't show here in this drawing, or I can't show, are that often, if you look around, you'll see ghosts, moldic pores of where these sponge spicules or radiolarians were. And it might be in a unit above it. There could even be a chert, actual layer of chert somewhere nearby. And all this material that, when it dissolved from opal amorphous, and got into the pore waters in the system, then they can reprecipitate and or usually replace things. So here they're most often replacing limestone. The pore waters have this situation where you can replace it locally with chert. And for instance here, this bedding plane, that can be a boundary where the pore waters are more easily moving through it, has more permeability, and so it's more prone to develop these nodules that are replacing the limestone. Another thing I've seen that's very common are the chert that's in the shape of burrows, shrimp burrows that were in the limestone. These shrimp burrows can get all these weird shapes and things, and they can just be all chert. And that makes sense too, because that's where fluids move through better, move through these burrows better. So you're more apt to replace and or precipitate chert within them.
Circling back to my observations so many years ago, we now understand that sponge spicules dissolved out of the rock, leaving only the shapes of their skeletal remains as voids in the rock to hold natural gas. This type of porosity is referred to as moldic porosity. It's pretty amazing to think that sponges could affect the lives of natives and animals so much, and that they even contribute to our modern lives in unforeseen avenues.
I've enjoyed exploring this topic with you. It's given me the opportunity to revisit some of the early days of my geology career. That's been fun. And also, I've had an opportunity to explore some avenues and pathways that I hadn't done before concerning this topic. I hope you've learned some too. Would you consider subscribing to my channel? Thank you for watching.